All right, so we're going to find the binding energy and the binding energy per nucleon of helium-4, right? So remember, helium-4, helium, when they give you stuff like this, right? Helium means that it's got 2 protons, right? Any atom that has 2 protons we call helium. By the way, the reason it's called helium, it literally means sun element, because they didn't discover helium on Earth. They discovered it from the spectral lines of the sun. But anyway, all right, that's more than we needed to know. So let's look at this thing, right? Helium is made out of basically, we're going to break this helium-4 molecule, right? Molecule, dear Lord, this atom, okay? We're going to break that down into a hydrogen and another hydrogen, right? This is helium, 4, 2, right? That's the number of protons and neutrons. That's the number of protons, right? Plus neutron plus neutron, okay? The mass of a neutron is actually in your packet, so you got that. And we're going to use this mass right there, okay? We're also going to use the fact that, sorry, one atomic mass unit, if you convert it to pure energy, is this many million electron volts, okay? We're also going to use this mass of hydrogen, which is the same as this, right? Oops. Okay. And there we go, right? Okay, so on this side, we've got a mass of 4.002603. And we're turning that into 2 hydrogens, right, which is 1.007825. And then 2 neutrons, 2 free neutrons, right? All right. So this side, by the way, when you take it all apart, the parts, paradoxically, but not really paradoxically, the parts have more mass than the atom together. And that's because if we went this way, if there was some nuclear reaction that would do this, okay, it would release energy, okay? Now, by the way, the more energy it releases, the more stable the atom, okay? The lower the potential energy, right? Higher potential energy is less stable. Lower potential energy is more stable, okay? So let's add up this side here. Let's go 2 times 1.007825. Definitely don't round these, right? Okay. Where did we get all that precision? 2 times 1.008665. We get this from those mass spectrometers that we talked about in the last chapter. Okay, so the taken apart mass of helium is 4.03298. Okay, when it's put together, it has a mass of 4.002603. So the mass defect here, right, is this minus this. So let's go minus 4.002603. And we get that the change in mass from here to here, right? Whoops, why did I write a W? Change in mass is 0.030377U, okay? You actually increase it, right? You'd have to put that much energy in to take the atom apart, okay? And then what we're going to do is multiply by 931.5, and we'll get this in MeV. So times 931.5, and that's 28.30. Yeah, it's 28. Let's see. Now we have 4 sig figs because of this, so it's 28.296. So I'm going to say 30 MeV. Okay. So what that represents is how much energy you'd have to put in to just tear apart this poor little atom. Okay. Now, per nucleon, since there are 4 nucleons, right? There's 4 nucleons. There's 4 nucleons, okay? We're going to divide by 4 nucleons. That's the mass number, right? Okay, so divide by 4, and we get 7.074, which really this is MeV per nucleon. And really that's an objective comparison of the stability of the helium atom, okay? Giant things like uranium-235 have huge binding energies, but when you break it down per nucleon, it's really not all that much, okay? So this will have, I'm not sure, I think it's maybe about on the order of, but things like iron have a whole lot of binding energy per nucleon, okay? Anyway, all right.